Seems good to me.
Good.
Um,
Okay, I'm ready.
One second. All right.
Hmm. We have
Can
merchandise.
we start, Ofek?
Yes.
Okay, great. So hi everybody. Um, so today I'm very happy to introduce our speaker who doesn't need too much of an introduction, but still, he's Ofek Birnholtz from Ilan University, and he's going to tell us about the Gravitational Wave Transient Catalog 4.0 overview and highlights. So please, Ofek.
Hi. Okay. Uh, Thank you. I'm going to talk mostly about the catalog. The catalog by now is almost outdated because it's the catalog reviewing all the events up to 04A. It came out in August, but since then, of course, we've had some trouble here in Israel. And the catalog number 5, covering events up to 04B, is expected to be released in about a month, in May. So we're releasing them quite more faster these days. But because of the situation, I haven't actually had a chance to give a talk about this catalog. I think except for local here at Bar Ilan and at the Open University. So I'm going to talk about the catalog, talk about the events, look a bit forward, give a few highlights of events from O4B, which we've already released, and kind of overview with a focus on tests of general relativity that we have performed and are performing with all of these events as they come. By we, of course, I mean the LIGO Virgo KAGRA collaboration. This is a huge collaboration. This work is definitely not entirely my own. I'll mention a few points where I did specific things, but this is a huge effort done by many, many people and supported by many, many groups and governments, mostly the NSF. So Trump actually is relevant. We got the Senate to block Trump from cutting our funding. Which is quite unusual and important these days. Shown here is kind of an overview of the event rate over the 4 observation runs we've had with the LIGO Virgo KAGRA collaboration from the September 2015 first detection here in 01 into 02, 03 in 2 parts. Now 04 has had 3 parts. And as I'll maybe mention later, there is expected to be another intermediate run between 04C and the long hiatus before 05, which is going to be probably called IR1 for intermediate run 1. For astrophysical reasons, we actually want to run this summer. So expect something to start around August or September for another kind of intermediate run after these. And of course, you'll see, yes.
This graph is number of events as a function of observation time?
Yes. Observation clock time. So you can see, obviously, there are breaks in the slope, and these represent the improvement in detector sensitivities in the long hiatuses we take between runs.
Thanks.
So we'll get to those a bit later. Also shown here on the right and bottom are spectrographs of 2 of the most prominent events from O4A, both of which we'll talk about some a bit more. GW 231123 and GW 230814, which was the brightest or the loudest event in O4A, and up to well into O4B, it was the loudest event ever. Okay, so as I said, the LIGO collaboration is very, very large. Our papers have about 1,700 authors in over 320 institutions in all continents by now, even have representatives in Africa. The detectors that participated in O4A, though, are basically only LIGO Hanford and LIGO Livingston, the 2 American detectors. Virgo was on partially for some of the time, but with sensitivity that wasn't very good. And it ended up not contributing scientific quality data to any event. So it was basically dropped from the analyses as out of observation mode. This has changed for O4B and O4C, where we have had LIGO participating and contributing. Looking forward, the main transition in the network that's expected. KAGRA is coming into operation and slowly increasing in its sensitivity, and it's improving its sensitivity, increasing in range. LIGO India is now being constructed after finally purchasing all the land and doing the legal stuff. They've got cement in the ground, building a LIGO machine in India. Virgo is improving, and GEO is no longer listed. The detector here near Hanover, Germany, is officially retiring from the network. Its arm length, or 600 meters long, which by now is a generation and a half ago, is no longer being maintained, and the Hanover group and most of the German groups are now shifting focus to working on LISA, the space detector, which we'll talk about next.
Ofek, can you explain what was the problem with Virgo and how they were fixing it?
There are two ways to think of that question. One is the technical issues, vacuum leaking and things, a mirror breaking and requiring a lot of modifications. There's the higher level to think of it, which is there's organizationally some problems going on. Virgo has had successive event failures and missed deadlines or missed target sensitivities over the past 10 plus years. It's instead of catching up to LIGO sensitivity, it's actually drifted away from LIGO sensitivity. So LIGO has been improving more than Virgo has been catching up. That's probably an institutional problem, which the collaboration is trying to fix by actually merging the LIGO, Virgo, and KAGRA collaborations into a single new collaboration called IGWEN, the International Gravitational-Wave Network, which is supposed to start to form and start working sometime this year, so before the end of 2026. If you start hearing that name buzzing around, it's a new hierarchical political organization to manage all the detectors and kind of bring the labs together so we can push the hardware better and get everyone on the same level sensitivity-wise.
So from what you're saying, it seems that Virgo will not be contributing much in the next few years.
No. So Virgo
No?
has been contributing for O4B and O4C. If you want, I can skip quite ahead to the estimated. Oh wait, not so much here. This is the O4A range. You can see Virgo is at the bottom and not very operational for a very long time. But in O4B, it's catching up. It's almost at 60 megaparsecs. It's got a uptime or duty cycle that's comparable with the LIGO detectors. We even have a significant time here, 29%, where we had 3 detectors operate together in science mode. So it's not that Virgo is not operational or not contributing. It's just that it's about a third of the range of the LIGO detectors.
Okay, thanks.
I mean, it contributes to fewer events and it gives us less information. Although sometimes that information is crucial because a third detector gives you better sky localization, which you cannot get even with just doubling LIGO detector sensitivity and range. You'd still get more from a contribution of a Virgo detector.
It sounds to me like a one-sentence summary could be Europe is falling behind the US as far as gravitational wave are concerned.
That's not accurate because the United Kingdom is actually part of LIGO, and so is Germany. For a very
So Virgo historically has seen this type of events, administrative and scientific, throughout its history. So that's why I was asking whether something has changed, and yeah, your answer reflects the situation.
So Virgo was the main forces behind Virgo are actually France and Italy, and a few other European countries, but Germany and the United Kingdom are LIGO members, and they're part of LIGO, not part of Virgo. Mostly, it's an institutional-based collaboration, not a national collaboration. It's not like CERN, but that's generally where things lie. So make of that what you will. But now there's there's an attempt to get things up. KAGRA also is lagging significantly behind. It wasn't even on the plots I showed because their range is around megaparsec order of. They have, so they're 2 orders of magnitude below LIGO. Okay, so we've done this. The papers, there are actually a bunch of them by now. All of these here have been submitted to a focus issue of AppJ Letters. Some have already been accepted, some have been published, some are still undergoing review. The last 3 to have been submitted are the 3 TGR papers, 1, 2, and 3 here. So we had many TGR tests. We split them into 3 papers. They were submitted about a month ago on March 20th. Those are the 3 papers for which I was the chief editor. So I'm more familiar with them, but these are all kind of different aspects of the same catalog, working on the same data, coming out more or less together. And you can see them already on the archive, and some of them have already been published.
Congratulations, Ishar Kochacha. Is chief editor the same as what was called coordinator?
So there's a paper writing team manager and a chief editor. I guess the coordinator is the paper writing team manager. I'm the number 2, basically. Okay, a lot of headaches, but that's also part of the job. Also out, not as part of the special focus issue, are specific event papers. So the first one to come out of 04A was 230529. This already came out in 2024. And was interesting as a mass gap event. So the lower object there was about 1.4 solar masses, typical for a neutron star, but the high mass object was well within the mass gap between neutron stars and black holes. So we don't know what it was. We have a separate TGR paper on that event, an interesting one. And 231123, whose spectrograph we saw on the first page, which looked so weird because it's the highest mass event to date. And as we'll see, high mass for a gravitational wave event means a very, very short time in our band, which means you don't get the nice chirp, or I guess your way would be this way. You don't get the nice long chirp. It looks a lot more glitchy and short. So there are a lot of analyses, issues and methodology and technical systematic problems going into analyzing such a short event. But definitely interesting because, again, the masses are well above what's expected, and basically the consensus is forming that this cannot be a first generation merger. There has to be multiple mergers hierarchically, and we'll talk about populations a bit further down. Also, I'll mention 3 events released already from 04B. They had their own papers, and we released them quite quickly. 250114 is, to date, the highest SNR, the loudest signal we've had, with an SNR of about 80. So that's twice the SNR of the runner-up 230814 here, the loudest 04A event, and already approaching 3 times as loud as the original GW 150914 in 2015. So sensitivity is improving, and we're still getting lucky every once in a while with very, very loud events. So it has its own paper on like the main results we can derive from it, testing the nature of Kerr black holes and the area theorem, and a specific additional list of tests, which we'll talk about a bit later. 24, 1011, and 1110 are this pair of binaries, completely unrelated to each other physically, cosmologically. They're from different patches of the sky, but they are similar in that both of them have very, very asymmetric high spins. One is prograde, one is retrograde, but these kind of break the usual, what we now call vanilla systems, where everything is non-spinning before the merger. So we've been busy this last couple of years, and we still are. Okay, so the basics for people not well into gravitational waves. Basically, what we have is 2 compact objects, M1 and M2. They orbit each other. As they orbit, they radiate gravitational waves according to the quadrupole formula, at least when they're far enough apart. You can substitute the quadrupole moment for 2-point masses and calculate the energy loss. You get it here from the Einstein's quadrupole formula, which is the general relativistic gravitational extension of the Larmor formula for dipole radiation and electromagnetism. This energy loss can only come at the expense of the mechanical energy of the orbit, which means that two objects sink to lower orbits, but as they do so, Kepler's law tells us that they will accelerate in their rotation. So the frequency increases, and you can kind of do the math and find that there's this particular mass combination, the chirp mass, similar to a harmonic mean of the two masses. And this particular combination is the only parameter that governs at the Newtonian or Keplerian limit the evolution of the system. So this would be the most important parameter in the in-spiral, and that's how we classify our systems, be they black holes or neutron stars or a black hole neutron star binary. We classify the frequency evolution as a function of frequency, and the important parameter is this chirp mass here. The chirp mass also determines from the frequency evolution, the length or the duration of the in-spiral. More accurately, as the in-spiral is nominally infinite, it determines how long the in-spiral will spend within our detector band. And that comes from here, and you can see that it's inversely related to the chirp mass. So again, high mass signals end very quickly. Low mass systems, like a binary neutron star, can last for minutes or even longer, depending on the sensitivity. The general morphology of the system appears here. We see that it increases in amplitude mildly, while dramatically increasing in frequency and shortening the period. Finally, we have this merger, which is the most violent part, and then finally a ring down to some quiescent, stationary, nominally should be Kerr black hole. Okay, the signal itself, the amplitude of the signal also scales like the chirp mass. That is, it's not the high mass that determines the signal amplitude. It's not the lowest one. It's this combination or harmonic mean between them, this chirp mass, and then it decays like R, which means if you want to calculate how far you can see something, it will depend on the chirp mass. You can see heavier systems to further out. It's not exactly linear in the chirp mass because there's also this effect coming from how long it spends in the band. So you get something like 5, 6 instead of a power of just 1, which doesn't seem like much, but if you calculate this in terms of volume rather than in terms of distance, then you get the third power, and you get that we're actually sensitive to almost similarly to the chirp mass to the power of 2.5, which means we have a very, very strong bias for seeing heavy systems far away, much more than low mass systems. And you can trace this, if you want, numerically here on the left. You can see chirp mass evaluated for different primary and secondary masses, and you can see the sensitive volume or event rate we can expect for these different masses. And you can see that there's also almost a factor of, this is probably 500 or so, or almost 1,000 between the higher mass systems and the low mass systems. And if you could follow this kind of clock diagram on the right, then time here goes from midnight clockwise in each observing run. Radial distance represents the actual observed distance from us. The size represents the mass, and the depth of color represents SNR. So obviously, near the center, we have these close systems, but we can see that we have further and further heavy systems the farther away you go. And as detector sensitivity increases from run to run, you see that we're getting kind of these bubbles drifting further, coming out from further and further out. Angularly, that is time-wise, you can see that they start to almost touch each other. So in O4A, we've had instances of multiple events per day. So the rate grows considerably as sensitivity grows. We're looking forward, of course, in O5 and later in LISA, we will have really overlapping signals. For LISA, they'll also be longer in duration, and we expect them to actually overlap with each other basically completely. Okay.
Does LIGO make Do they make a specific preparation for observing the overlap with Lisa? Do you have some kind of a connection or with ET or what have you?
There is a great overlap between the LIGO or IGWEN network and either Einstein Telescope, ET, or Cosmic Explorer, CE. Basically, all the Americans in LIGO are in some way involved in CE, and all of the Europeans are involved in ET. So there is a clear demarcation between Einstein Telescope and Cosmic Explorer people. Working groups, the collaboration in ET and EC is a bit more loose because they don't actually have equipment yet. ET, which is the collaboration I'm part of, and Shachar is also a member, and I don't know if Tzvi is a member. I don't know if anyone else here is officially an ET member. Einstein Telescope is now debating both its design, that is L shape or something else, triangle shape, and its location. There were originally for a long time two contenders. That's one of the things.
I meant some theoretical work to try and see whether you could combine, as you said, observation from Lisa and the others.
So there's no overlap between Lisa and LIGO because the bands and frequency are disjoint. However, everyone knows some loud LIGO sources will appear in Lisa before they appear in LIGO, and we do expect to have them kind of give us a guidance if LIGO is still in operation then, or more likely, if whatever succeeds LIGO is still in operation then. With ET, there is an overlap in frequencies, but the problem is somewhat different. The reason I mentioned the people are overlapping is because, of course, the same people are thinking about the same problems, and the problems we will face when we have overlapping signals will be that it's more difficult to estimate parameters when you have overlaps, and even before overlaps, when the sensitivity increases, so that the theoretical models are no longer good enough to explain away all the features from the noise. This is actually a problem that we thought we would encounter coming up to LIGO, to Lisa and ET, but as I'll show today, we are already encountering. So some of these, 230814, the SNR 42 event, already seems to have modeling systematics louder than the noise which it encountered. So we're starting to find things that look like deviations from GR, but we can, if we look deep enough, we see that it's actually traceable to the models not being good enough. And I can give you a kind of order of magnitude back of the envelope explanation as to why we're encountering this problem now and at these sensitivities. Rami, you were asking something, or you want to wait for later?
I said thanks.
Okay. So this is the detector network for 04 until 01 until 04A. You can see that Virgo was contributing at the end of 02, as everyone remembers. GW 170814 was the first 3 detector event, and then 170817 was the binary neutron star localizing the sky using 3 detectors. In 03, Virgo also contributed. We had 43% of the time as 3 detector network time. This went down for 04A, but as you saw in a glimpse before, is already going up for 04B. The sensitivities, you can follow their improvements, especially for the red and blue, so the LIGO detectors, getting further and further down. GEO and KAGRA are not shown here because, again, GEO is retiring, and KAGRA and GEO have both had very, very low sensitivities and ranges. Okay, this is kind of the plot summary for the uptime and the detector ranges. We're seeing an increase up to about 160 megaparsecs for 04A for the 2 LIGO detectors. Virgo is trailing behind, but has caught up with about a third of the sensitivity or range for 04B. And so in 04B, we've had useful 3 detector time. Virgo is not as sensitive as we would like it to be, It's not competitive with LIGO, but it's definitely complementing LIGO, for which we are thankful, and we're hoping it will improve further. Livingston has already reached, at some points, stable 180 megaparsec range, and these are calculated for nominal binary neutron star sources for historical reasons. As you remember, this means that we can find heavy binary black holes to much, much, much farther away. Right? This is calibrated to a 1.4 solar mass object. If we look at something like GW 5914, something that's a 3030 object, so that's 20 times higher in mass, so much higher in distance, and much, much higher event rate. Okay, and these explain the slope changes in this detection curve here in clock time on the right, and normalized to hypersensitive volume on the left. So the left and right show exactly the same events and exactly the same information, but on the left, it's normalized to the volume according to the sensitivity of the detectors. And then we can see that actually there's nothing funny happening in the universe. The reason this event rate is going up is directly traceable to the sensitivity of the detectors. This is kind of the plots that instrumentalists like to show every time they want a break in operations so that they can improve. Every time spent in improving the detectors pays for itself very quickly in a higher event rate, and it compensates for the time lost.
This is total of 13391 events up to 04C.
Up to including O4C, yes.
Up to including O4C. Do you have a similar plot with, say, events above 20 SNR or something like that? Something which also takes into account the improvement in the SNR?
I don't think one's made that plot, but it's easy to make because each catalog has a list of all events with their times and SNRs. So it's up to O4A, we haven't had that many events with SNR over 20, probably something on the order of less than 10 for O4A. So this specific figure would be very bumpy if you put the limit at 20. If you put the limit at 10, you'll get something that's smoother. Maybe until O4C, you'll already get something that's smoother, but I should say the O4B and O4C data here have asterisks, have stars between them, because these are alerts. They're not confirmed events. The catalogs are not out yet. O4B should be out in about a month. So there have been some, for example, in O4A, there were more than 128 alerts going out. Some of them are retracted. Some of them are actually found in offline analyses rather than online. So this is kind of an estimate of how many will be in the end, but these are not exact numbers for O4A and O4C. They are for the first O1 to O4A are exact numbers. Also worth mentioning is that O4A has finally 128 new events, and you can see that the total for these runs was 218. So we've more than doubled the number of events in this run, which was not exceptionally long. This is completely a payoff on the investment in improving the detectors. Of these, 86 have a low enough false alarm rate, or if you want high enough SNR, they're kind of related, to have merited full parameter estimation. So in the catalog, they will appear with all of their parameters listed. This is kind of an overview of the our binaries through time. For reference, you have the electromagnetically found black holes and neutron stars, and then the blue and orange are the LIGO events. This is up to GWTC3, so up to O3b. Each of these is, of course, two events, in this case, two black holes merging into a third heavier one. And for O4, we've more than doubled the amount of events. And some of the interesting ones, so this here at the top is 231123, the highest mass to date. You can see that the remnant is now above 200, and even the constituents are both expected to safely be at or above 100 solar masses. These two black hole neutron star event here, the orange and blue, this will be 230518 and 230529, which I mentioned. This is the mass gap event merging into with a neutron star, probably producing a black hole, but we don't actually know. So the bulk of events we find are kind of these middle ground ones, which by now we call vanilla in the collaboration. But every so often we get one of these kind of exceptional ones, and they usually get their own paper released quite fast, quite quickly, to allow astronomers to look at it and see what's going on. Okay, before we go further into depth, just a bit more about.
Just a silly question, maybe, but in this plot, is there a reason why it's kind of almost I mean, it has these two sides, and it's not organized by the weight of the resulting black hole? I mean, why are the heaviest ones in the middle?
Aesthetic reason, I think.
Aesthetic reason? Yeah.
Completely
Maybe.
aesthetic. If
Okay.
you organize these by detection time, then obviously, as expected, these are cosmologically distributed and uncorrelated. So you just get a mess of things all over the place. You can't make anything out.
Okay, so it's just a choice.
Just your aesthetics.
Yeah, okay.
Nothing in nature is this.
Yeah, no,
pretty.
I just did.
Right.
Okay.
Okay, modeling. So we talked a bit about the very, very early inspiral, where we use the quadruple formula kind of as is, assuming a Newtonian orbit. That, of course, is not completely correct. When the velocity increases to relativistic velocities, when the objects come closer and you get a gravitational potential, which is deeper, you need to introduce post-Newtonian modifications, which we've known how to do for in various orders for decades or more. Likewise, in the end state, we have the Tokowski equation and black hole perturbation theory. You expect to have a final black hole, a curved black hole, ringing down into some quiescent stationary curved black hole. So this is as represented in Kip Thorne's cartoon from the late 90s. We know this part at the time. We already had known this part. We had known this late part. There was a question as to what would happen in this non-linear dynamical regime of GR in the middle, represented by these kind of here be dragons plot. But of course, in 2005, we had Pretorius and others solve numerical relativistically on a computer the merger, and found that it's actually the gravitational wave is quite regular, and NR has completed this, and we've now connected the PN through this effective one-body regime to the quasi-normal mode regime. Smoothly and differentiably. So this is a regular waveform, and these numerical simulations now produce many more cycles backwards and forwards, and we don't use them directly because the cost of making a numerical relativity waveform simulation is very, very high, but we have approximants which match these waveforms, and we have many families of those, and they keep improving in time. We'll talk about a bit more of them later, and that's what actually goes into the machine, both for detecting these signals and for analyzing the parameters. So this math is known and is calculated with various effects and various accuracy, improving over time. Of course, nothing in nature is this pretty again. In reality, we have noise, and these signals are very weak. So on the right, we have kind of this time frequency plot, which, if you squint in the right angle, looks like what you'd expect from this bottom plot, a Fourier transform of the signal, this kind of Loch Ness monster shape. You can see it as a chirp, brightening, but of course, it's almost drowning in noise for all but the strongest signals. And if you look at it on the left side, even this plot of GW 150914 is not the raw data. This itself has been whitened. So the everything above about 500 hertz and below 30 or so hertz has been Fourier transformed and thrown out. This is a bandpass filter. Also, this right plot doesn't show what's above and below because it's just complete rubbish noise. The detector is only useful. Now it's been extended up to about 1 kilohertz, but still we have this band where we do what we do, making and analyzing the signal out of the noise. So this is what all of the new O4A events look like in these spectrographs. So again, time goes to the right, frequency goes up, and the intensity shows the energy in that frequency bin and time. And you can see these chirps. Some of them are more easily made out than others. For example, 230814, the brightest one in O4A, is very easy to pick out. You can see the chirp and probably estimate the parameters with a ruler and calculator. 231123 over here is much higher mass, much shorter time, looks kind of like a blob and a bit harder to make out. Some of these are nicer than others. The BNS ones are hard to make out by eye because they're very, very long. And so at each time, they're actually not very strong. But if you integrate it, they actually come out quite brightly. 230529 has an SNR of, I think, 11.6, which is not bad. Okay. The mass distributions, again, on this primary, secondary mass, and you should always keep in mind that there's a strong bias to the upper right. So high mass and similar, high equal masses are basically the most preferential or preferred, because then the chirp mass is highest and the range is highest, until you kind of see this 231123, which is alone, not necessarily because there are not many events there, but again, because this is already a signal that's so short, it's almost, most of the signal is dropping outside of the detector band. So we have a cutoff at these high frequencies. But then again, you have kind of all of this bulk around where the first detection was. It wasn't just lucky. Most of the events are clustered around this area. We do have another batch here, which you can kind of make out, and then stragglers down below. If you want to see it by total mass on the left, then you see again this clustering towards higher masses until the edge of the detector band. But you can see 230529 here in, I guess, light turquoise, and 230518, kind of these lone events at very low masses on the left. This red one is 231123 on the right. And a few other kind of noteworthy events are pointed out at this plot. If you look more accurately at the mass distribution features, for example, at the primary, you can sort of make out bumps and shallows. So peaks and troughs in this plot, features which digress from just a power law distribution. And this is more prominent if you look at it in the chirp mass, wrong direction. In the chirp mass plot, you can already see two things. One is you can see that we're narrowing down. You could also see that here, one up. From GWTC 3 to 4, we're narrowing down our error bars. So more events kind of highlight features in the distribution. And you can now see features in the population. And I presented this last August, and immediately someone in the audience jumped up and said, this matches my prediction. Okay, it half matches his prediction. He sort of correctly reproduces this overdensity peak at 25 solar masses, but exactly anti-reproduces this gap at 10 solar masses. So the people doing binary systems and binary evolutions of systems are looking into these plots, and now we're finally giving them enough data to actually make useful results, whether we affirm or rule out some other models.
Ofek, one more question. Sorry about that.
As many as you like.
So, as far as I remember, the highest Q that LIGO had before was about 30.
What do you mean by Q?
The mass ratio.
No. We never had a map. Oh, wait. 30. We can probably see that. You can see the Q here. So these lines are equal Q. This one would be
Anyhow, my question is whether you were able to detect high Q or small Q events at a higher rate.
No, you can see that the limit here is about just under 10.
Okay.
I think we use inverse Q to what you do.
Yeah.
But 10, just under 10 here.
And so the increased number has not moved that maximal Q above 10.
No, but I also should say that I don't know where you got the Q equals 13 number from. I think you might be confusing the LIGO detections with the numerical simulation catalogs. They typically go up to Q of 18, and the approximates appropriately go to Q of 18, and there are very few simulations with Q of either 32 or 64, but there are very few simulations.
Okay.
That means that the actual LIGO sensitivity, modeling-wise, decreases very, very strongly outside of the numerical relativity calibrated range. So we actually don't expect to see many of these systems for at least two reasons. One, the amplitude is much weaker because if Q is small, then the chirp mass is much lower than what would have been determined by the sum of the masses. And two, because modeling becomes problematic there.
Okay,
so
thanks.
So Q equals 10 is approximately, as you can see, the LIGO bound thus far. Okay, I think you were confusing with the catalogs, not with the simulation catalogs, not the observation catalogs.
In this case, I might have confused that with the Q for the ET. But so maybe I don't remember.
Okay. Spins are another interesting story. Most of our events, as you can see here, have basically zero spin. At least in O4A, the only O4A violators are here 231118 and 231028, which have mildly positive spins. You can also see that they're located on the higher chirp mass region, which might suggest that these are second generation mergers where you expect to have more spin because you have the remnant angular momentum from the first merger conserved as angular momentum spin of the progenitor of the next round. This red one is 2311.
Sorry. Could you remind us how this chi effective is defined exactly? What's the definition of this spin parameter?
You can think of it as a weighted average of the two spins of the black holes in the direction of the angular momentum of the orbit between them, but they're not weighted by masses. There's some overcompensation there because that's not. It's basically the combination that goes into the 1pn correction to the phasing evolution in the in spiral. If the masses are similar, it's basically just an average because the weights are almost the same, and that's the intuition you can have in your mind. Notice also for 231123, which again, although it had a very high SNR, so you'd expect parameters to be well constrained, it was a very short signal, and so even the spin and even the mass is all over the place. So a very loud signal, but very short, and this is the price that we pay. Okay, so let's talk more about this 231123 event. It has not about 20, mass over 200 solar masses, but as you can see, if you actually plot it, even whitening only gives you about 3 visible cycles. So these are very, very short signals. They match data. We have no doubt that it's real, but as for parameter inference and drawing any conclusions from it, it's caveat emptor. High masses and high spins are supported. High mass definitely. High spin is supported, but not necessarily. We do have, as we saw, 0 or negative spin in the 90% posterior. The progenitor is, interestingly, in this mass gap expected from pair instability supernovae, so we don't expect heavy stars to directly collapse to black holes heavy enough to produce this. We expect it to be either AGN environment induced or some hierarchical merger, and there are some references here. More interestingly,
can you go back, Ofek?
Yes.
Ofek. So why the error on the distance or the redshift is so high?
Because to know the distance, basically what we do is you calculate the waveform template or the waveform parameters. They give you the amplitude of the signal. You compare the amplitude of the expected simulated signal of the same parameters to the measured amplitude, and that ratio gives you the distance, right? Standard astrophysical, standard candle practice. You know what you expect to find in amplitude, you measure something, you find a distance from those. If you don't know the parameters accurately, you don't have a well-defined standard candle, the uncertainty in parameters translates to uncertainty in amplitude, which translates directly to an uncertainty in distance. Because these are black holes, we have no electromagnetic counterparts. We don't know where it comes from in the sky. And these distances, we can't even match it up with a galaxy or a catalog. So basically, all you have to go by is the amplitude, and any uncertainty in parameters translates immediately to uncertainty in distance, sky location, inclination angle. You can see all of these are very, very poorly constrained. Okay?
Yes. Although it seems that the error on many of the parameters is much smaller than the error on the distance. The error on the distance is about what, 100%.
Some parameters are better constrained than others depending on which part of the signal you observe. For example, for a low mass system, the inspiral will be very, very well observed. So the chirp mass would be accurate for 170817. It's accurate to, I think, 4 or 5 decimal points. On the contrary, if you have a high mass system like this one, the chirp mass is not very well constrained because it's very short. You don't have any inspiral. The good constraint will actually be on the final mass, or rather on some combination of the final mass and final spin, which determines the peak, the merger, and the ring down. So different things can be constrained by different types of physics for different signals.
Thanks.
Okay, another problem we have for this event, as it is so short, we find that it's actually, its analysis is not only sensitive to uncertainty in the parameters, it's also sensitive to uncertainty in which model we use. And we have different waveform families and different waveform approximate models, giving disjoint results. For example, for the mass and spin, mass and mass ratio, or two masses, these all translate to each other. And you can see that there's overlap between many of them, but not all. For example, this XP-HM, which is the phenomenological model, which includes precession and higher modes, gives you posteriors which are different in some of the parameters from the non-precessing symbols or the models without higher modes. We're at the point where this signal is so short that, okay, it's a two-pronged sword here. On the one hand, it's a very short signal, so you don't actually have much, a very good baseline of parameters. On the other hand, it's quite high in SNR, which means the models think they know it very well because the noise is low. So what's that? So you actually see here that it's the analysis tools that create a bigger problem than the noise itself, which basically means that we're at a point now, not ET, not Lisa, we're now at the point where we have signals whose interpretation differs based on waveform families and modeling. So this is kind of a, stop everything, back to the drawing board. We have to recalibrate numerical waveforms and waveform families. The sensitivity, our detector sensitivity is now better than our model sensitivity, than our model accuracy. For a long time, we've had predictions ahead of experiments. Now we have experiments ahead of predictions, which is an interesting time or experience to be at.
That is really great, I have to say. And but do you think now for numerical relativists the right thing to do is to go to the parameter range near these parameters that you find and just do a lot of simulations in that window and try to? I mean, is that the thing to do?
It's two things. One is going nearer to these parameter ranges, which were not in the original. Although, okay, so GR, as you know, has no mass scale, right? A signal should look the same at 10 solar masses, 100 solar masses, or 10,000 solar masses. The problem is the detectors are not the same at every frequency scale. So modeling errors which were allowable at certain ranges of the signal for vanilla events are no longer acceptable for these events. So it's not just about simulating the systems at higher masses. It's because the simulation doesn't care about the mass. it's simulating the physics relevant for a waveform whose morphology at this particular part of the signal is relevant for the masses that you have. And this will be a different challenge for, depending on your detector. ET will be different, LISA will be different, not because the physics of the source is different, but because the part of the physics to which you're sensitive is going to be different. The second thing, of course, is that there's more physics included as you have higher SNR, and you become sensitive to more effects. For example, precession and eccentricity, which, when you and I were students, everyone just ignored, because you want to look at the simplest, you want to detect one system, circular or quasi-circular, non-precessing, non-spinning even at the beginning. And now we're starting to see that maybe precession is important, maybe eccentricity is relevant, and these are kind of things that must be simulated and are very difficult to simulate, not only because they add parameters to an already high-dimensional parameter space, but because they change all sorts of numerical assumptions you could perform earlier. For example, eccentricity mixes up scales between the near and far regime, so it messes up your numerics. Precession introduces a whole new dimension, and now conservation works differently. So these are very, very difficult numerical relativity problems, which the field is now facing. 230814.
Sorry, so just to understand that. So, like, we know in principle how to simulate it. People know how to simulate it. In principle, it's just you need to cover many, like a much vaster parameter range, or is there like problems?
No,
are there problems in principle even in doing such simulations?
Doing the same simulation for more instances is usually easy, okay, unless they're exceptional. But that's, say, the easy part. But if you add physical parameters, they can break some assumptions. Okay, everyone knows the Einstein equation, but when you do it numerically, obviously you want to assume as many reasonable assumptions to simplify the model, right? You want to make it, I don't know, as planar as you can, because reduction in dimension means you don't have to solve n cubed but n squared cells in your simulation, right? Quasi-circular means that you're always only looking at basically one length scale, especially if the black holes are of similar size.
Mm-hmm.
And it's quasi-circular, you're always calculating in one scale. If you have eccentricity, you're now mixing up the near and far scales from the early signal. So this again introduces, either you use a finer grid from very early on, which is much more expensive, or you want to do some adaptive mesh refinement, but you're going to do it back and forth, and this dynamic itself introduces noise. Precession is even worse, because now you've got things out of plane, and you've got you can't just enforce conservation so easily, because you have exchange of angular momentum between the two objects and between the orbit. And these things are in principle the same Einstein equation, but the challenge of the Einstein equation, it took decades to solve because you needed to reduce it enough to be solvable on a grid. And now you're starting to introduce everything you neglected before. So it is a challenge. 230814 nominally is simpler than 231123 because it's twice the SNR 42, and it's longer. It's a 62 solar mass system. So this is a fourth of the mass of 231123, a third or a fourth of the mass, which means it's much longer in time. We don't have any edge effects. You can see it as a whitened waveform, and now you can actually follow it for multiple cycles. It's a beautiful waveform with a couple of caveats. One, it was a single detector event. Only Livingston was in operation. The mass ratio is completely standard, almost no effective spin. But even for this one, we detected that their waveform systematic problems might be related to it being a single detector event, might be related to something else. It might be just related to the fact that the SNR is so high that that systematics are surfacing. This is what I was hinting at before with kind of a back of the envelope calculation. A decade or a decade and a half ago, when LIGO was in design, everything people were looking at we were expecting to find something of an SNR 8 to 10 range. So Flanagan defined SNR 8 as kind of the threshold for detection. So we were looking for something on the order of SNR 10. And then it was said that, okay, we need waveforms to represent the physics. Obviously, no two waveforms will agree, and you can't put a full numerical simulation in the waveform approximant. So we'll define a mismatch level at about 3% mismatch, which for an SNR 10 event means that for what was defined as an acceptable criterion for 99% of your waveforms, you'll have a mismatch of something like 0.3 in SNR. So for almost all of your signals, you'll have the mismatch below the noise level, so you don't care about it, and it's an okay neglection to perform. But now we've got regular events. We have 100 events in O4A. Some of them are probing SNR 40, so 4 times higher than before. We're already an SNR mismatch or amplitude waveform mismatch of 3% at SNR 40 already means that your mismatch in modeling is comparable to the noise level. So again, this is another expression of the sensitivity of the detectors now being ahead of our models. And when we get further down to the ring down, we'll see that for that event, it actually creates a discrepancy in analyzing the ring down. It actually it looks wrong.
Ofek,
Yes.
if I look at the residuals, they look actually quite large, especially during the inspiral. And
Where
somehow I'm looking down at the noise. Yeah. So, and somehow at near the merger, it seems that they're very small. Can you explain that, or am I seeing something correctly? I mean, if I look at the light gray
Yeah, I think
residuals,
you could find this was already present if you look at the original, right? You see the 2-3 peak cycles look right on, but you see this much more noisy further out. This is related to the amplitude. The amplitude is maximal during the merger, and so the noise level seems negligible relative to the amplitude of the signal, while early on or later, the signal is weak, the noise is about the same, but relatively it looks bad.
so it's not something that is related to the way that you do the fit.
No, this is not just regular noise. The noise level is consistent. Okay. I think that this even quantifies it in terms of a sigma. If you imagine kind of this one sigma line, it should basically cover or rather, the number of peaks outside the one sigma line should be consistent with the sigma level, and you can do that statistics. It's consistent with the noise you'd expect.
Okay, thanks.
Okay, I mentioned EWTC 4 has all spins basically consistent with 0, but we will peak at O4B, where we have these kind of 2 interesting events, those twins, 24, 11, 10, and 24, 10, 11, which have confidently negative effective spin and confidently positive effective spin. So both well constrained and away from 0. So you can see kind of comparing all of the catalog GWCC4, and these stand out as the most exceptional in spins. So we are starting to find events which, for some reason, start off very, very highly spinning or even counter rotating, which is interesting, but that's okay. A peak at O4B events. We're quite far off, but I do want to talk a bit about test of GR. Obviously, GR goes into the modeling of all of these waveforms at every stage, and hence at every stage, we can introduce possible modifications. Modifications in the inspiral, which would typically be post-Newtonian modifications, modifications in the ring down, echoes which have been suggested, and many other consistency tests between inspiral and ring down and other such tests. We have 18 different tests performed on the GWTC4 catalog in 3 papers. So consistency tests is paper 1, parameterized tests in paper 2 of all sorts, and then tests of the remnant, either ring down tests or echo tests in paper 3. we narrow down the selection of events. We don't work on all 128 events in the 218 events in the catalog, but rather restrict ourselves only to 2 detector events with a false alarm rate under 1 per 1,000 years. So we only look at the really confident ones, and on top of those, each test can kind of impose its own selection criteria, what it would like to work on. For example, parameterized tests will usually look at in-spiral things. Ring down tests will look at the higher mass events, where most of the signal that we have is in the ring down. Let's skip this a bit. So we have, for example, a test of subdominant multiple amplitudes that is looking to compare the possible 3-3 mode to a possible 2-2 mode. And while this looks to be a very wide distribution, we see that actually the center is very close to 0. So about 0.2 or 0.3, 0.4. There's very high support for the subdominant mode to indeed be subdominant, as we would expect. The reason that there's also this negative block is because of counter-rotating modes. So when you only have 2 detectors, you don't know the direction of the orientation of the plane of orbit, and so you can flip between the pro and retrograde rotations. The polarization test is a simpler one. Here we imagine what would it look like if we had tensor, vector, or scalar polarizations, or any combination of them. And these are base vectors here on the left. And basically it shows that every combination of polarizations, not including the tensorial one, is very, very strongly disfavored. And anyone that does include the tensorial one is basically consistent with the 0 when adding a vector or adding a scalar or adding a vector and a scalar to the tensor don't really increase the base factor. They don't increase the probability that this is true. So in other words, scalar and vector are redundant when the tensor polarization is there and damaging when the tensor polarization is not there. So everything is consistent with tensorial polarizations as we expect in GR, and maybe not in other theories. The in-spiral merger ring down test asks the following question. Imagine you had the early part of the signal and then the late part of the signal, and you do parameter estimation on each one of them separately, not knowing about each other, and then compare if they produce the same final object. So that's represented as delta M final over M final, delta chi final over chi final, and you'd expect in GR all events to be around 0. So you'd expect the early and late predictions to agree with each other because GR doesn't change in the middle of the event. And indeed, you find that this happens with posteriors being wider or narrower depending on the SNR of the events, but basically all consistent with this 0-0 mark. So on mark, consistency is preserved, GR is salvaged. I added here on the right-hand side the plot from the 250114 paper, this SNR 80 event from O4B, because you can see just how much better it does single-handedly compared to the overall contribution from the entire DWTC4 catalog. So you have the individual DWTC4 events here in gray. You can see that this square, this block here, between minus 0.5 and 0.5 is kind of just the middle of this part. So we take a zoom in of all the best events of DWTC4, even they are much wider than DW250114, which on itself does much better and is bullseye on GR, which is a nice result. So this is
1 sigma, Ofek, these are 1 sigma contours?
These are 90% contours.
So it's 2-ish, something like 2 sigma.
1.5 sigma, I think, yeah, 95% would probably be 2 sigma. This is about 1.5 sigma. So this is 250114, again, a peak from O4B, an SNR 80 event. You can see it very clearly in the whitened data. Again, of course, there's noise before and after, but it gets swallowed in the peak of the event. And you can see it here in the, you can see it with your eyes in the spectrographs, and these are very, very clean parameters, very similar to 150914, but much sharper due to SNR, again, 3 times as high. For this one, we can actually do a ring down analysis of the post-merger, which is accurate enough to give us support for finding another mode. So here we're looking not just at the 220 mode, so the fundamental harmonic of the highest quasi-normal mode 2-2. We have the overtone, the first overtone, and it's located, or its estimated location is within the posteriors calculated by 2 different ring down pipelines. So of course, they're quite wide, much wider than the 220 mode, which is the dominant one and very well constrained. But it's consistent that this is the first, I think, the first measurement of an overtone, which we trust in an actual gravitational wave event. The frequency is where it should be. The damping time is where it should be, compared to the 220 mode. So we're happy. This very accurate measurement of the ring down is paired with a very accurate measurement of a long, nice in spiral, which means, again, we can do a consistency test between not just the final mass and spin predicted, but rather between the areas for these black holes in the early and late parts of the signal. And this is kind of the testing directly Hawking's area theorem. We calculate on the left side, we calculate first the sum of the areas of the 2 black holes before merger, then from the parameters of the masses and spins. Then we calculate the mass and spin of the final black hole, and from that its projected area, calculate the difference, and we see that it's first of all positive and consistent with what we'd expect from GR. So this gray line here is what GR predicts with the uncertainty in the parameters themselves with a full waveform. And the green is just looking only at the early part and only at the late part and seeing the difference between them. And this is a big improvement relative to what we had for 01. Here on the right, this was kind of the original measurement of the area theorem from gravitational wave paper, where you'd expect the area to grow. So a ratio of 1 was expected from the area growth. A limit of 4 is basically the most energy you can have before the maximal area per the given energy. So the early events at 01 sensitivity could not rule out area decrease, although it was maintaining energy conservation. Now we're very, very far away from area decrease, and in fact, you can effectively rule it out. The prior is also shown here. The prior actually favored area decrease, but we see that the data is telling us that, in this case, Hawking was not wrong. Parameter in spiral tester may be the most relevant, and I think that's probably time-wise the last thing I'll do before talking about the future. These are introducing modifications order by order in PN terms. So we take the in spiral waveform, we modify the phase evolution with this delta psi or delta phi, run parameter estimation with the modified waveforms, and we have these constraints in 2 different theories, or different models, FTI and Tiger, which also use different waveform families, but we find that they're basically consistent. And here we find that with GWC4, GR is maintained in all the PN parameters that we could test. The bounds get lower and lower. So compared here to the GWTC3 bounds and to individual events, you can see that we're getting better and better improvements between factors of 1.4 to 6.6, depending on the PN order. And these are the best results on PN constraints, definitely from 1 and above. In the low PN orders, there are actually specific systems which give better bounds than the entire catalog. For example, GW 230529, that mass gap event, because it's such low mass, does better at the low PN orders. So it's over here, beating the catalog at -1 PN. 170817, the binary neutron star, gives the best result both for -1 PN and for and it beats the catalog for 0.5 PN, although 230529 trails a bit behind. And of course, the binary pulsar, this is not a gravitational wave event detection. This is the classical observation, still beats everyone at -1 and 0 p.m. So I think by now they have decades of observation. So at 0 p.m. and -1, they're still the best. We also have a combination of the different runs. This is when you assume that the modifications can depend on system parameters. Here we have a principal component analysis, still all consistent with GR. Let's skip this. More interestingly, maybe, we have single events which beat the catalogs. So 250114 here in the blue star single-handedly beats most of the GWTC4 results, is still beaten by the BNS at -1 p.m. And 230814 itself, the highest O4A event, also beats many of the GWTC3 constraints and is competitive with a full catalog on its own. So again, there, as well as here for 230529, which beats the 3 and 4 catalogs respectively for 0.5 and -1 p.m. We still have these specific events which are either very high SNR or very low mass, which give us single-handedly better constraints than 100 others. Okay, so we're improving all the bounds. I think I'll have to skip many of the rest of these tests, except for saying that maybe we have a better bound now on the graviton mass, found from no dispersion in frequencies on these events. They come from very, very far away in cosmology, so they can accumulate a very, very long distance and phase if there were dispersion. We have found no dispersion, and so we have a better bound on the graviton mass. And I won't get to, I think, to talk about ring down, other than saying that for some events, for example, 230814, we find discrepancies. And these, again, we think are coming not from a problem in GR, but from modeling problems. And we've actually done a campaign of injecting waveforms of different families with similar parameters and repeating the tests on simulated data. And we find deviations. So this, of course, could have been found years ago, but detector sensitivity was not sufficient to merit this kind of test. And now, again, this is showing that detectors are now ahead of modeling, and we have some more modeling work to do. So it's interesting for the theorists and numerical relativity people again. Okay, I'll skip some of this stuff. Looking forward, we're expecting IR1 to start in the fall. So there will be another run. The agenda behind this was that we want a 3-detector run of LIGO with their Rubin online, so we can do follow-up of anything that we find. But of course, in the future, we have Cosmic Explorer and Ilan telescope, which you'd mentioned, already planned and expected in about a decade to work on the terrestrial frequency range. And we expect even before that, or around that time, LISA and Tianqin, the Chinese detector, to open up the frequency of the low frequency, the supermassive black hole regime in the sky. So there's a lot more coming up. We already know that we need more modeling to cover what we were already discovering, let alone what will happen in LISA and Cosmic Explorer and ET. So there's a lot of action expected, and we thank our sponsors, and I thank you for listening.
Thanks, Ofek, for a great talk.
Okay,
We had a lot of
question?
questions. Yes.
A small question. What does IR1 stand for in the next run, the name of the next run?
I think it's intermediate run 1, because it's between 04 and 05.
Okay. So the next one, the one after it will be 05.
05 is kind of always in the distance. We started 04 expecting 04A and 04B. Then we added 04C. Now we added IR1. Hopefully we will get to 05 at some point. And then maybe 06, and then hopefully transition smoothly to Cosmic Explorer and Einstein Telescope. We're still building another LIGO detector in India, so it won't be alone. We'll still run our LIGO things before Cosmic Explorer and Einstein Telescope come up. But we expect to have more and more of these.
I understand the construction in India is just at its beginning.
Yes.
All right, any more questions? Well, yeah, I have also small questions about modeling. I know that people are starting to talk now about also environmental effects, adding that into the modeling of waveforms. So at what point, at what SNR is this expected to start being important?
Just a moment. Depends on what environmental effects and how strong they are. So one of the slides I skipped, I don't know if this is what you meant by environmental effects,
Like,
but
I don't know.
lenside acceleration, for example, is a test that doesn't probe what's in the environment between the black holes, rather it tests the environment in which the black holes are, as in if they are, as we expect should happen from these hierarchical mergers of higher generations, you expect some AGN environment or some environment that's drawing many of these stars and black holes together. You might expect that as they merge, they're also orbiting this supermassive black hole. And so you might have acceleration of the system itself, right? So not something coming intrinsically from the two objects, but from the environment in which they're seated or in which they're moving. And we now have a test for this in paper 2 for the two events that allow for this test to be performed. And while the errors are quite large, we don't find any line of sight acceleration at the accuracy which we have performed. If you're rather looking at the environment between the two black holes, that is, if they're merging in a dusty environment or a gaseous environment or something like that, some of those can be mapped, especially in the in-spiral, to some coefficients. You can look at those, or if you have you want to put in drag or something like that, you can see if it's directly translatable for an existing PN bound, or if not, write a new pipeline and we can run that as well. Or you can run it. The data is all public. The catalog data has been public since August when it was released on arXiv. The TGR results are public as well from about 3 weeks ago. So everything is available for everyone. It's an NSF funded project. Everything is publicly open data.
All right, thank you. So, okay, unless there are any other questions, maybe I'll stop the recording and then we can ask Ofek in private. So let's thank Ofek again for a great talk.